Alright, and here we are with solving systems of equations with me, Mr. Hain. And our essential question for this part of the video is, when should I use the addition method? What is the addition method? Building drama for the future. And when should I use the substitution or graphing methods instead? So we'll talk about that as we go along through this video. And until then, let's dive right in. Okay, so the addition method is a method that we use specifically when we see that we have variables with opposite signs that cancel easily if we add the equations together. So in example 1, I see that I have a positive y and a negative y, which means that if I were to add these two equations together, the y's cancel. X plus x is 2x, and 4 plus 6 is 10. Now, because the y's cancel, I can solve for x. By dividing by 2 on each side, I actually see that x is equal to 5. Now, here's the thing. We know that the solution to a system of equations, if it exists, is just where the coordinate point where the lines cross. So I'm going to take this x, which I solved by eliminating the y, and substitute it back into the first equation. So instead of x plus y equals 4, I have 5 plus y equals 4. By subtracting 5 from each side, I see that I have y is equal to negative 1. And so because I have an x and I have a y, then kaboom, I know the coordinate point where both of those lines cross. And that coordinate point is 5 comma negative 1. Awesome. So let's take a look at example 2. So for example 2, I also see that I have y's with opposite signs. So y is going to be the easiest one for me to isolate here, but I need to do a multiplication of the first equation by 5. Now why did I choose 5? Because this is a positive 5y, so I want them to cancel easily. So the easiest way is if I multiply the first equation by 5. So when I multiply the first equation by 5, I have 15x minus 5y equals 55. Remember, this 5 multiplies each term in the equation. I bring the second equation underneath, and now I see that if I add them together, the y's will cancel. I have negative 5y and positive 5y. So 15 plus 2 is 17, and 55 plus 13 is 68. I didn't realize it until I checked with my calculator, but 68 divided by 17 is equal to 4. And we have a spoiler alert with this y is equal to 1, so let's get there. I'm going to plug that 4 into the first equation, and I get 3 times 4 minus y equals 11. 3 times 4 is 12. Subtract the 12 from each side, I have negative y is equal to negative 1. So if negative y is negative 1, then the opposite of y is negative 1, then y must be positive 1. There's our little spoiler. And I have x and I have y, so I have a coordinate 4 comma 1. Kaboom. Go ahead and try checkpoint 1 and checkpoint 2. Pause the video and I'll be here when you get back. Use the same method that I used in example 1 and 2. So let's do some more examples for the addition method. So I like these because I see that I have opposite signs for my y. But here's the thing. I got to multiply the top equation. So let me multiply the top equation by 4. And when I do, I have positive 8y and negative 8y. So I can add these together, and I have 21x equals 168. So again, the 4 multiplies each term in the top equation. Beautiful. So that means that now I can divide by 21, and x is equal to 8. Again, all I'm going to do is take this x coordinate, and I'm going to substitute it into one of the equations, and that will give me 3 times 8 plus 2y equals 48, or 24 plus 2y. I'm just isolating for the y, and when I do, that coordinate point for y, x is 8 comma 12, or I mean y is 12. So 8 comma 12 is where those two lines intersect. Awesome. So example 4 is a little bit jacked up, and here's why. Guys, I don't have everything like I do neatly over here, all of the x and the y on the left-hand side. So what I'm going to do is I'm going to move the y over by subtracting. So that would be 2x minus 7y equals negative 17. And then I'm going to add this 3x to both sides, giving me 3x plus 5y equals 17. All right, so if I do that, I've got these equations. And here I see I can multiply. There's a reason behind this, and I'll show you. I'm going to get rid of my x's. So I'm going to multiply the first equation by -3 and the bottom equation by +2. The reason I'm going to do that is because that will give me -6 in the top equation and +6 in the bottom equation for the coefficients of x. That lets me cancel. So I add these together. Of course, I have 31y is equal to 85, and that is a nasty fraction. But I'm cool with that because I'm not even going to substitute back in. What I'm going to do is I'm going to change the numbers that I multiply by to cancel the y's, and that gets me the x value. So if I multiply the top equation, I've got 10x minus 35y equals -85. And the bottom equation, 21x plus 35y equals 119. And the y's cancel. Again, leaving me with the x variable isolated, which allows me to find the value of the x coordinate. And when I do that, even though I have two fractions, I never plugged in a fraction to find it. I just canceled again and isolated a different variable. So I know that my solution is 34 over 31, comma 85 over 31. Beautiful. So try checkpoint 3 and checkpoint 4. Checkpoint 4 is a little tricky. Remember, I moved the variables all to one side so I could cancel easily. If everything's lined up, it's a lot easier to see what we can add and subtract or have to multiply by. So go ahead and do that for checkpoint 4 and work out checkpoint 3. Leave this up, pause the video. I'll be here when you get back. So now we got some more examples for the addition method. And so I'm going to look at example 5. And when I look at example 5, everything's positive. I'm going to have to multiply. So I'm going to choose. I'm actually just going to isolate and get rid of the x variable. So I'm going to multiply the top by -3 because -3 times 4 is -12. And 2 times 6 is +12. So I'm isolating the y variable and I'm eliminating the x variable. So I've multiplied through. I'm going to add the two equations together, and something weird happened. On the way to trying to eliminate the x variable, I got opposite signs for the y variable, and now when I add the equations together, I have 0 equals -12. Okay, so there's no variables. So what I got to think is this statement true? Does 0 equal -12? And I'm sure that you're just yelling at your computer or TV screen here, and you're saying, like, dude, it doesn't. And you're right, it doesn't. That means there's no solution. Okay, so that leads us to example 6. And I'm going to multiply the top equation by +2 because, see, that will eliminate. That'll give me 4x and -4x. So I'm going to multiply the top equation by 2. And again, something weird happens. When I did that and I add the equations together, everything eliminates everywhere. So I have 0 equals 0. Same situation. I'm going to ask myself, does 0 equal 0? And you're screaming at your tablet, phone, computer, TV screen. You're saying, yes, it does cancel. It does, 0 does equal 0. And if 0 is equal to 0 and that statement is true, it's an identity. There's infinite solutions. These are actually the same exact equation. Boom. Sorry, I skipped ahead. Try checkpoint 5 and checkpoint 6. Go ahead and pause the video and use the same methods that I did in example 5 and example 6. Pause the video. I'll be here when you get back. And we're back with systems of inequalities with me, Mr. Hain. So our central question is, how does my knowledge of graphing equations help me solve systems of inequalities? So we're going to be graphing a lot. So let's take a look. So I'm going to graph in example 1, and however you're used to graphing, you can go ahead and graph. But really what ends up happening is I graph both lines. This is the graph of the first line, a y-intercept of 4, and the slope is actually going to be +2 because I've divided with a negative. So up 2 over 1. So I've graphed this dashed line because the inequality does not have an or equal to. So that becomes y is greater than positive 2x minus 4. So which is why I have the -4 here, and I have the y-intercept, and that is my line. Because it's greater than, I know this line is true above that line. So above the line right here is where it is true. So pardon my skipping ahead with my fingers here as I'm recording. The second line as I graph is going to be this solid line here. And that's going to be y is equal to -x minus 1. So I have -1 here as my y-intercept, -x, so down 1 over 1. And I know that it is greater than or equal to, so I have this solid line. So now that I have this solid line, I know that this is greater than, so it shades above that line. And the only place both equations are true is in this upper V region. And that's why when I isolate it, we have this as our solution set. And this is an open dot because the dashed line means that the dot is not actually where they intersect part of the solution. Excellent. Go ahead and try checkpoint 1. Graph however you're used to graphing and see what your solution looks like. Remember that the final solution is going to be where the two graphs overlap their shaded sections. Go ahead and pause the video so that you have my example 1 as a reference, and I'll be here when you get back. All right, so let's dive right in with example 2. And these are already isolated for us in slope-intercept form for the first one, and then the x variable for the second one. So what I'm going to do is I'm going to graph using slope-intercept. So my y-intercept is 1, and my slope is 1 over 1. Y-intercept is 1, slope 1 over 1. You see a solid line because, or equal to. And now for the second equation, I only have x is greater than 2. So I only have an x coordinate, which is 2. So I have a vertical line when I have an x. And since I know it's greater than, that means it shades to the right because that's where the numbers get bigger. So back to the other equation, the first one, it's also greater than, so it shades upwards. So now that we have both, the only places it's true where both would shade. So the first equation, the blue line here, shades up. And the red line, or the second equation, x is greater than or equal to 2, shades to the right. And the only place they overlap is in that upper V section. And because both of them are or equal to, we have a closed dot. So go ahead and graph checkpoint 2 using my example 2 as a reference. I'll be here when you get back. And ladies and gentlemen, as you can see by the black screen, that is the end of our video for today. And until next time, keep doing the math.